So it's good to mention that environment with following characters was created in the spray cabinet, and the uncoated anchor plate that came directly out of the foundry after only 24 hours present corrosion, and virtually the whole area was compromised. And I was surprised with this result because I thought that the plate would behave better. Now, the second plate to be tested was one with black oxidation coating. The results showed that after only 24 hours, the element present corrosion, and a good portion of the area of the anchor plate was compromised. However, as we see here, the coating obtained low efficiency. The third plate to be tested was one with KTL. The results showed after almost 200 hours the element present corrosion and in few points. The test stop criterion was the identification of corrosion, even if a minimal. This was strict criterion. Then the fourth plate to be tested was the one with hybrid coating. The results showed that after almost 700 hours, the element present corrosion in a few points as well. And the test stop criterion is the same. Identification, a minimum point of corrosion. Only for your reference, in the test with strains, the PT coating should protect the element for 1,000 hours, but it is accepted that 0.3% of exposure area has indications of rust, red corrosion. Then here we are with the conclusions. I will show you the main ones. The anchorage zones plays an important role in unbounded post-tension and deserve special attention. The Brazilian standard NBR needs to define more clearly which type of protection method to be used in pre-stressed concrete. KTL and hybrid coating showed uniform thickness and excellent adhesion to the base of material. The use of accelerated tests such as salt spray are good too to evaluate the behavior of coating subject aggressive environments. And the salt spray test applied to uncoated anchor plate showed an important warning in just 24 hours of exposure. And to finish, the salt spray test applied to the anchor plate with hybrid coating showed good protection, presenting corrosion with 772 hours to be precision. And the cost of coatings were booked, black oxidation 28 cents per part, KTL 32 cents, and hybrid coating 55 cents per part. I believe that's it. Should you have questions, I will be glad to answer them. Thank you very much. Slowly, please.
How was, and I may have missed it, how was the coating applied? Can this be field touched up? Or are these a dipped coating?
We are testing several coatings with more thickness to increase the hours. We believe that when I increase the thickness, I reach more hours.
No, if the coating is damaged during installation in the field,
okay,
can you touch up the coating?
Okay, for example, the hybrid coating with epoxy and polyester has you can management, you can use and manipulate, has a good protection to when you hit in installations. Now we are testing this, and the other problem is the wedge. We are testing is a good point because when you put the epoxy, we need to evaluate a new behavior, and we are testing in WG with John.
So protecting anchor is fine. How is it going to be integrated with the rest of the system, like the strand and the wedges, transition, the whole assembly of the anchorage?
This is we know that encapsulate tendon is the best at this point, and this study is only because in Brazil it's very difficult to have encapsulate tendons. Then we need to start a new research about this protection, and I believe that we can good values. Okay, that's it. Okay, yes. $24 uncoated, 24 hours coated with black oxidation, and almost 200 hours with KTL, and hybrid coating almost 700.
And really quick too, some of the tricks like the one to the US. Instead aplica, você pode aplicar isso fora ou tem que ser uma máquina. Você pode fazer tudo que você está fazendo na obra, ou você tem que fazer exatamente o que você tem que fazer antes. Pode fazer tudo que você está fazendo na obra mesmo.
Okay.
Apply it during the job site in the US. So.
Okay. With black oxidation is a process. Then you clean the anchor plate and make the process. Is industrial. We have many tanks with the chemical products, and is a sequence. One tank, second, and the end, the final tank, the piece. We have the coat with black oxidation. With KTL, you put up is the same of black oxidation, but in other sequence. Is a electrochemical process, and the hybrid we use first KTL, put KTL first on material on the anchor plate, and after powder gun of powder, and this gun has the powder input in the anchor plate, and after goes to a heat with a temperature almost 200 degrees Celsius for 15, 30 minutes. Evan, depois você puder traduzir para mim.
Good morning.
Okay.
Sorry. Which level of protection you are targeting? This is 1P or 2? What will be the end results? What you are looking for?
Okay. My goal is more than 1,000 hours because I compare with the PT coating and the area, the minimum effect, for example, in strength is 0.3% of the area. And I believe that when we increase it, the coating, the results will be better. This is only first test. Okay. Thanks so much. Sorry for bothering you.
All right. Excellent presentation, Fabio. Next presentation is about unbounded tandem finishing. We have two speakers, Ted Neff and Sam Cornell of GTI. Let me just try to introduce Ted and Sam briefly. Ted Neff joined GTI in 2018. And we all know that before then, he served as the executive director of PTI for 18 years. Previously, he managed his own consulting firm and worked for U.S. Department of Transportation with the Urban Mass Transportation Administration and Federal Highway Administration. And he's a member of ACI 423, 222, and 301. And he's the chair of the ACI subcommittee of 423G, which is about the ACI specification for unbound distinguished tandem. And he's a fellow of PTI, ACI, and FIB. Sam Cornell is the director of construction services for GTI. And he provides technical support, expertise to GTI's customers. Sam has been in PT industry for 43 years. In terms of equipment operation, repair, fabrication, extrusion, multi-strand, monostrand, stressing, tendon cutting. And he joined GTI in 2005. Before then, he was with the Suncoast Post Tension. And before that, he was with VSL for 23 years. Wow, very long career. I'd like to welcome Ted.
Thank you, Thomas. Pleasure to be here this morning. Sam and I will be talking about a subject that probably receives the least amount of attention out in construction, and probably in many cases is one of the more important aspects of installation in terms of ensuring the durability of unbonded post-tension tendons. You've seen the required slides, so run through these quickly. In terms of learning objectives, we basically want to run through the various finishing operations, give you an understanding of where things can go wrong, end up with some recommendations and guidance, hopefully, to improve the reliability of unbonded tendon systems. Just a quick outline of our talk. Start with the beginning, really protecting the tendons before we begin the finishing operations, trimming the tendon tails to the proper length and the different methods that are typically used for that operation, capping of the tendon tails after the cutting, and then the final step in the process, grouting the stressing pockets. And so at the end, we'll again give some recommended practices and hopefully answer some of your questions. What are we trying to do? Basically, the big problem, or potential problem with an unbonded tendon is water getting into the system. If we can keep water out of the tendon, the durability is tremendous, and the tendon can last indefinitely in many different exposure conditions. If water's allowed into the tendon, underneath the sheathing, into the anchorage, into the anchor cavity, we have the potential, we don't always see it, but we have the potential for corrosion of the tendon. And where we've seen isolated problems with post-tensioning, it's generally because water has gotten into the anchorage. And so our finishing operations are all geared to basically complete the tendon in a proper manner that ends up keeping this moisture away from the pre-stressing steel, the anchorage components, and everything that potentially could corrode. These are some recommendations from ACI in terms of, Fabio mentioned an ACI document on corrosion protection of unbonded tendons. This is a bullet list that is published by ACI in terms of steps that should be taken to protect an unbonded tendon. The items in blue are the ones that I feel are impacted by our finishing operations. And so all of these things can be impacted if we do by doing either the right thing and basically minimizing the potential of problem, or doing the wrong thing and increasing the potential for problem. The others are more system design and important, but not something we really deal with in the field. And if we look back at the history of unbonded tendons, we can see what the impact of water in the tendon can be. This is an old generation sheathing, I think it's a paper wrapped type sheathing, but those systems were very prone to water getting into the tendon, and a lot of corrosion problems. Those that are involved in repair are out there fixing these type of structures extensively. Now, obviously, we don't see water in our unbonded systems to this degree with today's state-of-the-art systems, but it does give us an understanding of what water can do to the tendon. If we trap water in an unbonded tendon, long-term, the PT coating will emulsify. With our good coatings, it takes a while, but if it's trapped in the system, we have that potential. And the system starts to break down over time. So that long-term durability that we all want, we want to give to our customers and the public is at risk. And again, it doesn't always happen, but the potential is there. One of the first things we need to pay attention to is protecting the tendon prior to the finishing operations. These are basically some spec requirements that are common both to the PTI 10.2 spec and the ACI 423.7 specification. Wording's a little bit different, but basically very similar requirements. The first is the timing aspect, and everyone recognizes that this isn't always adhered to, this requirement, but the concept that everyone, the intent of the spec and the concept everyone should be aware is the sooner we can finish the tendon and close it off to moisture, the better. And so we don't always make the one working day, and this is one working day after the engineer has approved the elongations and allowed the tendon to be cut. So it's not one day after it's been installed. Typically, it's after the engineer has given the okay to go ahead. And we don't always meet this, but the idea here, and the reason it's in the spec, even though it's not always adhered to, we don't want contractors taking 6 months and leaving that anchor open. And this gives the engineer of record a spec basis to basically get that cutting operation completed. And so the concept to keep in your head is the sooner the better. And if it's not a day, it should be as close to a day as possible. But the spec basically, both specifications do require that you protect the components within 1 day. Again, it's not done. There's a general statement, prevent water from entering the tendons. This one's pretty much ignored. I don't really know many people who do anything to protect the tendons during the installation, but I'll talk a little bit about some things that you can do later. And then and the third point you see there, if it's going to be an extended period, and there's, you have phase construction, we have reasons why you cannot finish the tendon, then the specifications require that some kind of protection unspecified in that protection should be taken. Again, this is not done very often, but it's the purpose of our presentation today. Sam and I are going to try to show you why taking these steps will improve the reliability of these systems. Potential problems, obvious one, if we haven't capped and trimmed the tendon, we can potentially get water into the system while it's open. Some parts of the country, not a big risk. Definitely a potential problem if you're on the coast, you're in the Northwest where you get a lot of rain, your rainy season, water getting into an open anchorage is definitely a potential if it's exposed for any length of time. That in turn can, unprotected anchorages can corrode while they're waiting for finishing, and rust bleeding and staining of the concrete is a potential issue, more of an aesthetic issue, but still can be an important problem that we need to deal with. This is just a graphic that had from some previous presentations, but water can get into, approach the anchor, blown by rain, and again, it's not going to happen on every project, not going to be a problem in every project, but where it is, and particularly when combined with other construction problems, has led to some serious problems and examples of where we haven't gotten the performance we desire out of unbonded tendon systems. This is an example of the corrosion that can occur, if you leave the pocket open for an extended period. Normal construction cycles, you're not going to get this much corrosion on the tail, but if it's 6 months in a de-icing salt environment, getting salt spray on the coast, you could see this when you come back to the tendon to finish it off later. Again, it's a situational thing. It's not going to happen all the time, But if we finish the tendons in a timely manner, this isn't ever going to be a problem for us. But just to be aware that as long as it's sitting there unfinished, you know, the unprotected components are subject to corrosion, and moisture will kick that off. And if it's salt-laden moisture, it's going to happen even quicker. There are some ways you can protect that end if it's going to be an extended period. These aren't used frequently, but there are devices available. These are just some protection caps that snap over the strand and slip into the anchor cavity and attach to the anchor. And they're just intended to be a temporary closure to keep moisture out of the anchor cavity. Again, we don't see these often, but it's the kind of thing that's available. And you'd consider, if you know, for example, you're going to have a stage construction, you won't be doing the second part of the construction for, you know, 6 months, a year, whatever, then something like this would make a lot of sense, just to keep water out of the system and you know, protect it. Because otherwise, if it's open, you're starting to see the corrosion issues. And even beyond that, you've got the issues of the water that's gotten into the system that you don't see. And that's a concern as well. When you trap water, when we finish the thing, we'll close it off. But if there's already water in the anchor cavity, in the tendon, in the sleeve, then that's not going to typically come out. Another useful way to deal with this is to leave the sheathing on until you're ready to stress the tendon. There are a couple ways to do this. You can pre-cut it and just leave the sheathing on. This isn't often done, but it can be, and you just run it through. What this does is basically helps fill that void where you pull off the sheathing while it's open. So there's not really a place for water to get into behind the anchor. And so this is one way to do it. You can also put the sheathing through, and there's special cutters available that will cut the sheathing at the back of the anchor. And this is just an example where, unfortunately, it's black sheathing, so you can't really see it. But if you look over, if you could see this, if we had a different color sheathing, this is this sheathed tendon over here, and then this sheathing on this side will be trimmed off, and then the tendon will be stressed. But in the meantime, this steel and the space behind the anchor is essentially filled with sheathing. And so it helps keep water out of the system and behind the anchor. It doesn't protect the anchor cavity, so you still have some areas that are unprotected, but it's a useful approach, and there are systems where you can do this, and it is being done, as you can see from the photos. So just some recommendations for protection prior to finishing. Using a system like I just showed you is one thing that can be done, particularly for extended exposures. Using protective caps of some type is another. The last bullet, again, you don't see it very often, because it's kind of a pain in the butt, frankly, to be covering tendon tails while you're waiting to be finishing. But again, you need to think about, if it's going to be an extended period, and months, you really need, and the specs really call for, taking steps to keep the moisture out of the open tendon. In terms of trimming or cutting of the tendon tails after we've stressed, here are the specification requirements. Again, we have a fairly tight timing. We got 1 day after acceptance of the stressing record, so we're basically waiting for the approval from the engineer. Again, it's the same concept. We want to try to get this done as quickly as possible. This should not happen 6 weeks after. This part's probably the least problematic because most contractors want to move forward as quickly as they can. So this one is probably faces the least resistance out in the field, but it is an important one. The length of the tendon tail is important, and it's got to be a length that won't interfere with an encapsulation cap if we're using an encapsulated anchor. And so basically this is the trimming of tendon tails is a very important aspect, and we'll talk about some of the different ways that you do that. Various cutting methods are used. First is the acetylene flame cutting, what we typically call torch cutting. This is probably the most common, been used for probably since the beginning of the industry. And slab on ground applications, abrasive wheel cutting is pretty common. There are also new technologies, plasma cutter, which is a more directed, confined flame type of cutting, and then a shear type of cutter. This is an example of a torch cutting. Again, this is probably the most common thing that's been used in the last 50 years. But as you'll see in a few slides, there are the potential problems with this kind of system. With a well-trained operator, this can work well, but the problem we have is, particularly in the labor market we have in construction these days, we're not always getting trained operators, and problems can result. Abrasive wheel cutting is a very fast method, cheap method that's used in slab on ground. The big problem with this system is the cover. As you can see with an abrasive wheel, you're not getting very deep in the pocket. And so this type of system is not used at all for encapsulated systems because you can't get the required cover. With slab on ground, we permit less cover, and there's a step you can take to when you don't have even the minimum cover. But basically, this is used because it's cheap and fast. But lacking that cover does create some problems, which I'll mention later. This is a type of plasma cutter, just to give you an operate. Sam's going to walk you through the proper operation. Like anything else, if this type of system's used, it needs to be done properly. So he'll kind of walk through that system. And then shears of various types are used to basically shear the cable. And this is, again, Sam has the expertise and knows the kind of problems that occur when this kind of system is used. So these are the four major types of cutting. The industry, I think we really need to focus on improving this operation. And again, I'll run through some of the issues. In terms of the problems, one of the common ones is we cut the tail too long, which in the old days of standard not encapsulated tendons wasn't that big an issue. Occasionally having a long tendon tail would not be an issue. But with encapsulation, you'll see it can cause a big problem trying to get that watertight cap onto the system. There's a lot of heat with torch cutting, and this can be a problem for the plastic components of encapsulation. And then the timing, because of the heated components, is hard to adhere to. And then if the operator is not skilled, you can end up with some significant residue in the pocket. So these are some of the things that can happen. We don't see it too often. That there is a potential cutting it too short, which would limit your ability for liftoffs and things like that. That's not a big problem, but we don't want to cut it too short either. But too long, we're not going to get cover. We're not going to get the cap on. And if we don't get the cap on, all the investment in encapsulation is wasted because it's no longer a watertight system and water can get in through the anchorage. And so the life of that tendon is going to be compromised depending on how severe the environment is. This is an example of how the heat, if they keep the flame in the pocket too long, you can see there's no chance you're going to get a cap on that and create a watertight seal. And so we've destroyed basically the effectiveness of the encapsulation system with the heat from this system. This is an example, I don't know if you can make it out, but this is black residue from the torch. The spec says clean the pockets prior to grouting. I can pretty much attest that I don't know that I've ever seen it clean to the degree that would take this off, but I'm sure it has, but it's pretty rare that someone would take that much time to clean. So this is going to interfere with the bond with the grout material and the surrounding concrete. And if it's not well bonded, it's not going to keep the water out of the system long term. Somebody gets really carried away, they can damage the anchor. And the problem with all these things is not that just the fact that they're occurring, but they're not easy fixes when they do occur. If you destroy the encapsulation system, you only have a couple options. You can try to remove it, which is a very expensive, timely process, or put in something trying to create a waterproof, some kind of real high quality epoxy or something like that. But it's not an easy process. So we want to avoid it. An anchor damage like this, obviously we're going to get structural failure. But this is more of an extreme. Somebody really didn't know what they were doing. But it shows you the impact, the heat that a torch cutter can have if it's not done properly. I'm going to turn it over to Sam to kind of walk through both the plasma cutter and shear cutter operation and talk about some of the tips on how that's done properly. And then we'll come back and look at some of the other operations.
Thank you, Ted. Good morning, everybody. Thank you for attending. I will be talking about equipment available currently in the marketplace for finishing tendons. And please, this equipment that we'll be discussing is important to only use it only after the tendon has been stressed and approvals have been given, if approvals are required. I see this a lot. So this here, which I'm looking at, is a plasma pocket former. Critical that when using this piece of equipment that pocket former is used. The slide, the picture in the center, you'll see the torch in there. The earlier slide shows it has a stainless steel shield in the front of it. So when you put that torch into the pocket, it bottoms out. And when you make that cut, it's cutting consistently at 5/8 of an inch. Gives you plenty of room to put a grease cap on. There's the shield there, plasma cutter. Comes with a 50-foot lead, and what the lead is, what makes the connection between the plasma and the torch, available in 100-foot also out there. Air compressor, plasma, all secured on a hand cart for easy moving around on the job. So in a plasma cutter, it's a very effective way, very quick way to cut your tendons within 5 seconds to cut using a plasma cutter. Very fast, easy to move around on the deck for cutting. Here's a good shot. Location of pocket formers in the proper direction, larger end down, allows the torch and shield to go in with the lead on it for your cutting. Now this photo, you'll see these sparks. You're probably thinking, hey, it's no different than acetylene, using oxygen and acetylene for cutting your tendons. But let me tell you guys, if you guys were to take a white piece of paper, put it on the deck there, and do that cut, it would not burn that paper at all. It's so hot and cools so quickly. Finishing. Another method is the pocket shear, battery and hydraulic. Using this equipment, guys, is real important that they're using the correct pocket formers. If you don't use the right pocket formers, allow that nose to get in there, you'll never cut the tail short enough to get your grease caps on. Also, if there's nails sticking out, you got to remove those nails to get that in there to do that cut. Two types available, hydraulic, and here is the battery operated one. Same scenario, you need to be using the correct pocket formers, allow that nose to get deep in and touching the face of that anchor. Very quick cut. Oh, I go back.
Let me just summarize here, in terms of our recommendations for recommended practice for trimming, particularly for encapsulated tendons, definitely we recommend avoiding torch cutting and abrasive wheel cutting if at all possible. And recognize, obviously, this is the most common technique out there. But it's important that we start paying attention to this and the potential for problems. I didn't really, the third bullet out here, out west, fire danger now is an issue with any kind of flame cutting, to the point that some jurisdictions require having a person assigned as a fire watch on a project, so that's extra labor. In those kind of situations, something like shear cutting, where flame is not involved, has some definite advantages. Clearly that's not everywhere across the country or all applications, but where you have fire danger, the last thing you want to do is end up being responsible for starting a fire someplace and all the liability that goes with that. And then, Sam hit on a couple items, and that's really why we wanted Sam to come through and talk about the operation. Using some of these newer technologies, it's like anything else, it has to be done right and using the right accessories with it. But when they're done right, they are very fast, very clean, and very consistent, which is, I think, good for our final operations. So that's really our recommendations for trimming and cutting of tendon tails. The next aspect of finishing is capping, there's actually a capping requirement for slab on ground with non-encapsulated anchors, which I'll mention in a moment. But these are the spec requirements from ACI and PTI that you see on most projects. Again, there's a timing requirement. And we had some discussion yesterday. I'm not sure PTI is 8 hours, but I think it is. But this is probably the most important timing consideration in finishing. Once we've cut the tendon tail, we need to get that cap on as quickly as possible, because that closes off the system. The grouting is important, but if the cap's not on there and not on there properly, the system's not watertight. And so we want to come as close to this 8 hours. Well, I think we had discussion yesterday in the M10 committee, maybe 24 hours is probably more feasible. But again, the concept, the quicker, the better that we put that cap on. And so that's an important consideration. The cap needs to be filled with PT coating or grease. And the reason for that is we don't want a place for water to collect inside the system. You know, if everything is done right, there won't be any water inside the system. But if we don't get the cap on perfectly and there's no grease in the cap, that's an area where water can collect. Condensation, seepage, whatever. So we want to have the proper amount of grease in the cap. And then I'll briefly talk, when we do use like the abrasive wheel cutting for slab on ground with non-encapsulated anchors, there are spec requirements that we put on a protective cap when the cover is less than 3/4 of an inch. Again, this isn't done everywhere, but it's in the specs. And when I get there, I'll talk out here in California, it is being done because there have been a lot of lawsuits that result from not doing it, and the rust bleeding that can occur when you don't have adequate cover and you don't have anything on the tendon tail. Some of the problems you can run into with capping, you know, closely related to tendon tail cutting. We don't have the right fit. We can't get the cap installed properly so that it's watertight. If we use the wrong cap or if things aren't right, we don't get enough cover and don't meet spec requirements. ACI requirements, PTI requirements require a minimum of 1 inch cover over the encapsulation cap. So regardless of what system we use, you have to have that minimum if it's something like a building or that like. Again, slab on ground is a little bit different, but anything subject to 318 building code requirements, IBC would require that 1 inch minimum. Some of our recommendations, the specs actually call for a mechanically interlocked cap. And what we're talking about here is in the past, we've used caps that were basically a friction fit, just held in place by friction. And the problem with those is, you know, vibration on the structure, transportation, you know, those caps can come loose. They don't always hold in place. And so the specs, both PTI and ACI, have been revised in the last decade to require some kind of mechanical connection so that it's not just held by friction. Now we have a lot of debate, what does that mean, mechanically interlocked, but in effect, some kind of lug or system that holds it in place. Caps, we recommend using caps with pre-measured PT coating. Again, if you don't, you know, messing with grease out in the field, first off, it's probably never going to happen. It's going to be a mess, and the chances of getting the right amount of grease are pretty low. And this relates again to the tip length of the tendon tail. If we have the wrong length of the tendon tail, then in all likelihood, the amount of grease in the cap is not correct. And so it would be one of two things. If the tendon tail is too long, the grease is going to come out of the cap and probably seep out of the concrete. If it's too short, then there's going to be an area that's not filled with grease and the like. So we need to use the right amount of coating, and you know, most suppliers provide a pre-measured amount of grease that's sealed off in the cap, and so that's a recommendation. Then there are different caps, and you want to make sure you use the right one to get the cover. This is an example of our cap with the pre-measured grease piece of, I think it's something like cellophane. I don't know if it's actually cellophane, but that holds the grease in place and then is punctured by the strand when you apply it to or install it on the anchor. You want to make sure that you basically put the cap on correctly. In this case, you want to, if it takes a rotation of the cap to engage the mechanical interlock, in this case, the lugs would be an indication if it's been rotated. But again, if someone's not looking at this and not paying attention, they can just snap it in place. It's not really connected. And again, we risk losing that watertight connection. Again, different types of caps, fixed ends, stressing ends, intermediate. There may be different caps for a particular manufacturer, and you just want to use the right one in the right application to make sure you have the right amount of cover. This is an example of one of those protective caps for slab on ground. From a corrosion standpoint, frankly, they're not worth much. But what we're trying to do is just basically delay the surface corrosion of the tendon tail, which can cause rust bleeding. And this isn't necessarily a performance problem. I mean, this doesn't mean the tendon's going to fail, but there have been a lot of lawsuits, particularly here in California, where rust bleeding on the edge of a slab in a residence leads to a series of lawsuits in a subdivision, and they just kind of go down each house and look for rust bleeding, and to the point that most of the PT companies now supply this at least in the California area, because they don't want the lawsuits. Again, it's more of an aesthetic issue, but you think about a homeowner, you don't really want a slab with a bunch of tendon tails bleeding out the edge. So that's why it's in the specification. But from a corrosion performance point of view, long term, if you had de-icing salts or things like that, it really wouldn't provide a high degree of protection because the tendon is not encapsulated. But just recognize that you do have that spec requirement if you have less than 3/4 of an inch cover. And if you have less than that, then you are at risk of not being in compliance with the applicable specifications. So the last operation I want to cover is grouting of stressing pockets. I'm going to try to go through, I'm not going to go through everything, but we've got a couple aspects. We want to use the right material. We want to use a non-shrink, or at least some would argue there's no such thing, but at least a low shrink grout. We recommend, if you can, using a pre-mixed material, just to get the mixture right. But it's important. One of the important things is to inspect the anchorages prior to the grouting operation. Some of the things I showed you earlier with the debris and damage, if once it's covered up with grout, nobody's ever going to see that. And so you can hide various sins very quickly with the grouting. And so to make sure we don't have those problems, we need to look at it before we start applying the grout. Again, we got the timing. In my view, this timing, one day after the cutting, is the least important of the timing considerations. Once we get the cap on there, we really have a fairly watertight system. We want to get the grout in there, and that gives us another layer of protection long term. But if we've got the cap on right, the 1 day part is not as critical as the capping operation. But again, the concept's same. We want to get it on as quickly. We want to get it done as quickly as possible. We've seen various problems in the grouting. This is obviously a pretty poor Example, the material, we get shrinkage, poor bond, inadequate cover, permeable, low strength grout. If it's not well bonded, water can go in around the edges of the grout pocket. This is an example. It may be a little hard to see, but you can see efflorescence at the bottom of these grout pockets. That's an indication that there's some water moving in that area. And so that's not a well bonded grout plug, and it's not doing a great job of keeping the water out of the system. There's some permeable grout. It's obviously going right through it. We're starting to see rust bleeding through the grouting. And again, it may not be a big problem, but it's certainly going to undermine our long-term durability. And in the right situation, aggressive environments, this would be a big problem. Low strength, we used to talk about a quality control for grouting being the kick test. You kick it, and if it falls out, it's no good, and if it stays in, it's okay. But there are many instances where the material is so poor that it doesn't even stay in the pocket. I don't see a lot of this, but it can also crack through shrinkage. And if we have a tendon failure, somebody cuts a tendon, plumber cuts a tendon, I think we've all heard about tendons popping out, but it also is an indication of the bond that we have, that the grout plug generally comes out intact. And so some of our recommended practice, obviously preparing and cleaning the grout pocket using the right material. One that we promote is using some kind of shear keyway or some other means, but a shear keyway is a system that we've developed that does this. And then mixing the material in a proper manner so you get the performance that's there. This is a pocket that needs to be cleaned, and this is why it's difficult. You got grease, you got debris from the torch, and it's going to take some effort to get that clean enough to get a good bond with concrete. So just the typical bond of a conical grout plug in a typical construction situation is something that has to be considered. This is an example of and it's not the only way to do it. I've heard of systems where you can ream a keyway, but in this particular system, it's basically a plastic ring that's slipped over the pocket former and then forms a keyway in the grout pocket. And just an example how it fits over various pocket formers. We did a quick test to see how effective this was. This is an informal pull-out test that GTI did. And this is a well-grouted, clean pocket with a conventional grout plug. We did the same thing with this pocket former with one of these shear keyways. The interesting thing is the other one, if you look, pulled out as a plug. Basically, not very little surrounding concrete came with it. This one, in fact, the plug did not pull out and actually sheared the surrounding concrete. So in summary, basically, there are several things. None of these are big things. Most of them are common sense things, but it's really a matter of awareness of what can go wrong and just paying attention to some of these details to basically ensure that we get the tendons finished the way that we intend to and maximize the long-term durability of the tendon. And some of the ways we do that, we protect them before we finish them, we trim them in a proper manner, get the caps on, we clean and grout properly, And then the last one that I'd encourage, and it's probably, again, receives the least amount of inspection attention. We should be looking at least at a representative sample of the finishing work, both before and after grouting. And it's probably not done in most cases. What we want is something that's finished properly, gives us an intact water-resistant plug. As I mentioned, inspection, part of the problem, particularly something like high-rise, if you're up 20 stories looking on the edge of a building, there aren't many inspectors who want to be hanging over a building looking at pockets. But I just throw this one in because this is one inspector's way of simplifying, coming up with a method of looking quickly at pockets. But it's important that we at least look at a sampling so that we know that the operation's being done correctly. And I want to leave you with one last thought here. Clearly, we haven't, a lot of these practices that I've talked about that have potential issues have worked well for us over the years. And poor practice can, at times, work. But the point I'd like to leave you with is if we really want a high degree of reliability in ensuring our long-term durability, we need to basically embrace some of these better practices. And they do exist. And I think if we demand those better practices, they'll become routine. And with that, I want to leave you, we want to avoid these kind of things. They're not common, but as an industry, we don't want this ever to happen. We want to be basically the model of good performance and long-term durability. So I thank you. Be happy to address any questions. And Sam, you want to join me up here in case I can throw you to the wolves?
Normally you come up here for a question. I don't have a question. I want to express my appreciation for you folks bringing this out, that I'm afraid that we'll leave the room and next year and the year after, we will not have addressed to these issues. Like you brought up transportation, and there are most folks, not my company, keep the tendon like this, goes through rain and snow. And that's how it was done 20 years ago, last year and this year. At the intermediate construction joint, the sheathing is cut and is left for a week. The water will travel in. And I could keep on going. So I would request that we should together in the industry come up with solutions, a list how we can prevent these problems happening. For example, flame cutting. I don't know how many jobs, how many stressing ends they melt the plastic. If it doesn't get reported, it didn't happen. So that's all I'd say.
Thank you, Rutin. Any other questions or comments? I appreciate your patience. We have a longer presentation than most of the speakers, so you have to put up with this one.
So I have a question with the cutting. So this would be a Sam question.
Good.
So with cutting with either a plasma or a shear or a torch, from a safety standpoint, what can you do to make sure that you don't fall off a building as an individual or cutting the tendon and so on? So what is it that we can do as an industry? What can they do?
Sorry. Larry, anytime you're on the deck and stressing, cutting, whatever, you want to have, if you're on the deck, a tie-off support and a hand available. So cutting with the plasma, you're just using one hand off the side of the deck and you're using the other hand to support yourself. The same with the battery shear, that you're asking.
Yeah, from a safety aspect. So you should always have a free hand.
Absolutely,
basically.
Yeah.
Okay.
So we're down to our last minute. So
I have a question for Ted.
Okay. I have an answer for you.
Okay, so when you showed the grouting the pockets and so on, we talked about what you had to do for preparation. The one thing that you didn't really talk about and didn't indicate was there's the precast plugs that are used, and there's some certain requirements when you use the precast plugs that have to be done. So could you sort of expand on that?
I'll be quick because I just got the buzzer 000. But real quick, the precast plugs are very good for providing high quality, impermeable material. But my concern about those, they're very dependent on the bond of the epoxy to the pocket. And epoxies are very temperature dependent. They're very moisture dependent. And the cleaning issues that I showed you, if you've got debris, you're putting epoxy over it. And then the final concern I have is when you put a grout plug into a pocket that's full of basically air, that air has to move out. And the only way it can move out with the with the precast grout plug is form a channel through the epoxy at the side. So there's no way for that air to escape. And I think we need to do some water intrusion tests to see what kind of actual barrier we're providing by the epoxy. The grout plug itself is fantastic. It's high quality concrete, does away with all the problems of the mixing and permeability issues. The concern is if you look at ACI for grouting concrete to concrete basically, the requirements are very extensive, and none of that is currently, in my view, been done with the precast plugs. So there are some issues that, not that they can't be overcome, but I don't think it's a panacea that fixes all our problems. We're past our time, so.
Where's Thomas? Oh, there he is.
Thank you.
Yeah, it's not my question. It's a question from the audience in the virtual.
We have time for it?
Yeah. Oh, yeah, it's okay.
Okay, sorry.
What is?
I'm just holding to your time.
Yeah, I think we have extra
I
minutes.
went Bryce hit
Yeah.
me with a whip here.
Yeah, last question. Yeah. But it's two. What is the downside of using plasma and shear cutter? That was the first question. Second question is shear cutter taking more than 5 seconds to cut?
Okay. Do you want to take
Pocket
that?
shear takes 5 seconds. By the time you're in the pocket, when you commit, guys, to make that cut, you pull that trigger and you let it do its job. You don't let up, you don't back off, and you cut the tenon within 5 seconds. All right?
The first question was, what is the downside of the shear and plasma?
Well, one downside, consider that people have to buy equipment. That's generally the biggest objection is
Vibration issues.
vibration.
Yeah, shear cutter.
No, it's a rotating. If you saw the equipment right grabs the strand.
Yeah,
and
you've got on a shear, either hydraulic or battery, there's a stationary shear that's in the nose, then you've got a rotating, and it's real critical that using a shear, battery or hydraulic, that cable is locked off. There's a locking nut on the back of that device that if it's not locked off, guys, that cable from the front nose where you're making that cut to the back, that cable, the 7 wires, it's twisting and rotating. It cannot do that. It's got to be stationary, and then let that shear just make that cut without the cable unwinding and damaging your rotating blades. It's got to be used correctly.
And I'm getting this from hearing Sam talk to customers and things, but the plasma, requires a power source, and it's got to be the right power source, so that isn't necessarily a downside, but it's something that people have to invest in, and so that's generally considered one of the obstacles is they've got to get the right power supply, buy the equipment,
And, you know, so.
Yeah, and really quickly on the plasma cutter, guys. That the plasma is single phase 208, 220. It requires 30 amps. And you know, I've been on so many jobs where that's the only problem with the plasma. You have that power, you're cutting under 5 seconds, and it's fast. You're in the pocket, you don't even have to be looking at it, side of the deck, leaning over, not even leaning over, just you can feel that the shield touch the face of that anchor, you fire, and you can just count 1,001, 1,002, 3, and it's done. The cable then will not just fall because you had the ground clamp on that, so it's right there, you pull it back in and you're on your way. Very quick. If you have the power, I would use it, guys. It is very fast. But again, power on job sites, they'll say yeah, they have it. They have the voltage, not the amps. Everybody's pulled into one box. You're up there. So on our unit, we have an amp now installed on it. So the first thing I do on training on a job, turn it on. I got the voltage. And then I just do a test cut on a piece of rebar. And if I'm not drawing the amps, shut it down, go to the contractor, get somebody up there to get you the amps. And believe me, guys, it'll be quick, very fast.
Okay, luckily we have a 25 minutes. Oops. I don't have a, okay, backside. The last presentation is about fire evaluating. We have two speakers, Ms. Tracy Nassau, Associate Principal of WJE Chicago office. She has 17 years of experience of investigation, repair, strengthening, high-rise towers, parking structures, plazas, pools, and remediation, construction documents, and so on. She's a registered professional structural engineer of 5 states, and she serves as the chair of a PTIDC AV committee and CRT 60. It's about the repair. And she's a member of ACI, ASC, and COE. Yeah. And second speaker is Ralph Leistico with WJE in Raleigh office. He has a 34-year of career. He's involved in numerous investigations, repair, designs, high-rise building, low-rise building, commercial underground structures, regarding post-tension, precast, RC, and also metal structures. And he's a registered professional structural engineer in 7 states and serves as chair of ACI Committee 224 about the cracking, as a member of AC and ICRI, International Concrete Repair Institute. With that, I'd like to welcome Ms. Tracy Nassau.
Good morning. Tracy called me back in January and she said, you know, I need somebody on stage with gray hair and somebody that stays cool under fire. And I know I got one of those covered. So anyway, staying cool under fire, we're going to talk about fire investigations of post-tension structures this morning. You guys got this covered. So what are we going to talk about? We're going to talk about knowing basically what kind of codes and guides are out there that you can rely on as resources to do fire investigations and for design. Just understanding the typical scope for fire damage investigation, specifically talking about PT structures, and also interpreting basically heat indicators. And that's basically looking at the area that's impacted and the surrounding areas for signs of what the heat level might have been. So you can determine potentially the limits of damage to the post-tensioning or the structure itself. So these are just some general resources. Like the seismic design codes, a lot of things are going basically to performance-based codes, and including the ASCE documents. Those are mainly design references. The ACI 216 document that we listed there is really more, gives you information about fire investigations, more specifics that we cover here. We reference some of those things, and I encourage you to look at those. So we're going to talk about where do we start basically doing a fire investigation. These are kind of the subjects we're going to cover. Basically estimating temperatures and duration, and then evaluating the potential changes in material properties. And then some of the testing that could be done, more destructive maybe things, or non-destructive testing, sampling and such. And then maybe what analysis would be appropriate, and the repair approach. This is kind of one of the things that's been happening throughout the country is podium slab construction, and with wood construction on top. And this was basically a fire. It actually was out here on the West Coast, and is somewhat typical. People setting fires actually, while these are being constructed. And you can kind of see there's quite a bit of material. And the reason we show it is kind of the source, the type, the duration of the heat exposure is pretty important when you're looking at fire investigations. So like in a parking deck, for instance, you would be looking at cars. It'd be a short burst of time. You have a high ignition potential fuel source. But looking at the duration and the type of heat being generated by whatever is the combustible is pretty important to understand. So, looking at some of the non-structural elements becomes important. That's kind of the first step really in an investigation that we typically would take. Kind of on the bottom left, you kind of can see in the parking deck, this was actually a recent fire in a parking deck that was actually a sweeper that caught on fire and burned for quite some time, but you can see the plastic sign basically melted, which kind of gives you some indications as to what the temperatures might have been. The middle one was actually an investigation that I was involved in where there was alleged fire damage, and you can kind of see the blue internet wiring that's still intact, which kind of gives you a clue that maybe there wasn't so much heat. On the right, you can kind of see the grout pockets. These weren't actually grouted, but you can actually see the grease caps melted. So that gives you an indication again, as far as plastics, what they might do. And you guys have probably seen,